We're going to have a go here at solving trigonometric equations. Now, trig equations really are this melting pot of all the different skills we've learned in trigonometry. It's using our exact values. It's using degrees and or radians or converting between them. It's finding angles in different quadrants. It's finding acute related angles. And it might even be throwing in a little bit of trigonometric identities that we'll look at in another video. But really, trig equations throws together all those non-triangle skills that we've learned so far. So let's have a look at what a trig equation really looks like, because you've seen these before, you just don't know you've seen them before, and you haven't viewed them in this light before. So a trig equation is just like an algebraic equation, where we might be solving 2x plus 1 equals 5. Well, a trig equation might be something like this. In its really most basic form, where I'm solving something like cosine of x equals a half. Now, the difference with a trig equation is that we could go straight away and say, well, I could go press the shift button on my calculator and I could find an answer, okay? And I could find where that is. Or I could look at this and say, well, hold on, I don't even need to do that. I can just look at that and say, well, that's 60 degrees. You might say, well, or I could go turn that into radians. So I'd divide it by 180 and multiply it by pi, and I'd get pi over 3. Okay, so if I wanted to answer in degrees, it would be 60, or in radians, it would be pi over 3. But you've actually missed something there. Okay, you're not wrong, but that's only the first answer. Thinking about what a cosine curve looks like, okay, if we were dealing with a triangle, that's our answer. Okay, if we were presenting a triangle here, we're just trying to solve this equation. So if I think about what my cosine curve looks like, it looks like this. Okay, it's got an unrestricted domain. It's got a range between 1 and -1, and I've just drawn the positive values here. It continues infinitely symmetrically in the negative direction as well. Of course, y equals cosine x being an even function. Now, if I think about what I'm actually trying to do here, most equations that we deal with are in some way, even if we don't represent them this way, a result of simultaneous equations. So if I draw this line, a half in here, y equals a half, blue dotted line, you might start to get an idea of what our issue is. Okay, our issue is that we found this first solution here. We have dealt with this guy here. That's 60 degrees. But we've actually got more solutions. We've got one there. We've got one there. We've got another one here. We've got another one here. We would have negative ones as well. We'd have one about there if we were dealing with negative angles. Okay, and this actually has an infinite number of solutions. Okay, so we cannot name how many solutions there are. So the first thing about a trig equation, we have to restrict the domain. Okay, we have to restrict the domain. That just tells us, well, we're only looking for answers in this zone. Normally we deal with x is between 360 and 0. It's our most common type, or we could write that in radians and say x is between 0 and 2 pi. It means exactly the same thing, just whether we're operating in radians or degrees. Going to have to be very comfortable with operating in radians more than degrees for solving these type of equations. So if we think about this, if we recall that I make one wave every 360 degrees, I'm just looking at this first part of my curve. Okay, everything between the red line and the green line there. So it means I'm going to have two solutions, and they're going to be these ones. Got one here, one here. We've already found the first one, which is pi over 3. This second one, if we think back to our all stations 2 central, okay, which trig ratios are positive in which of our quadrants? Well, we are talking where cosine is positive, so we're in quadrant 4. We're somewhere between 270, which is here, and 360, which is here. Now, how do we find an angle in the fourth quadrant? Well, if I'm dealing with degrees, I would say 360 minus my acute angle, and that would mean I could also have x equals 300 degrees. And those would be my two solutions. If I was dealing with this in radians, I would say 2 pi minus pi over 3, which would be 5 pi over 3. So my two solutions in radians would be pi over 3 and 5 pi over 3. Now that's how we solve our most basic version of a trigonometric equation. Now you're not normally going to be solving that in degrees and radians, you'll be dealing with one or the other. And always have a look at your domain to see whether the solutions you're actually finding fit within your domain. 0 to 360 or 0 to 2 pi are your most common ones, but we could have negative 360 to positive 360, 0 to 180. We could have negative 180 to positive 180. We could have a lot of different variations on this. And depending on how we're dealing with things, we might actually have to restrict some solutions as well. We've got two examples here, and in each of our cases, our first thing to do is to make our trigonometric ratio the subject. Okay, so if we have a look here, I've got tan x plus 1 equals 0. My first step is going to be writing tan x equals minus 1, because I've now got my ratio as my subject. Now, I can go straight to my calculator, but particularly if I've got a negative value in there, be very wary. Okay, you could get a negative answer here. By the way, for both of these equations, we're going to be solving between 0 and 2 pi. That's where our solution set is going to lie. Okay, between 0 and 2 pi, we're going to answer in radians here. We could answer in degrees as well if we'd like, but I'm saying we're going to answer in radians. So I've got tan x equals negative 1. Now, my first thing I ask myself is, what's my acute related angle? Okay, well, what angle is going to give me a trigonometric ratio of 1? I'm going to ignore the negative to start with and bring it back in at the end. Well, my acute solution is 45 degrees or pi over 4. Got to be comfortable with those exact values. Now, that's actually not an answer. Okay, that's not an answer because tan of pi over 4 would give me positive 1. I don't want that. Okay, but what it means is I'm going to have solutions in quadrants 2 and quadrant 4, because that's where tan is negative, to where sine and cosine are positive respectively. So that means my solutions are going to be in quadrant 2, I'm going to have pi minus pi over 4, which is 3 pi over 4. And in quadrant 4, I'm going to have 2 pi minus pi over 4, which is 7 pi over 4. And those are my two answers. Should label them correctly. X equals. We end up with two solutions. And if we were to go and graph y equals tan x, and then see where that intersects with y equals negative 1, you'll find it happens to us when we're looking only between 0 and 2 pi, or 0 and 360 degrees. Okay, so that's our thought process. First, I make my ratio the subject. I go and find my acute related angle, even if it's not a solution. Of course, if it's a solution, if we were looking for tan x equals 1 here, we could just go and say pi over 4 is our answer, and x equals pi over 4, and then find it in the third quadrant instead of the second and fourth. But here, be very careful, because pi over 4 is actually not one of our answers that we're looking for. It's just what our answers are related to. Once we've found our acute related angle, we go and consider which quadrants I'm in and how do I find the angles in those quadrants respectively, using our 180 minus, 180 plus, and 360 minus for quadrants 2, 3, and 4 in degrees, and then pi minus, pi plus, and 2 pi minus in quadrants 2, 3, and 4 respectively in radians. Now let's do the same thing again here. I'm going to go and make sine x my subject. I've got a sine squared x, which we're going to end up taking the square root of. We've got to be very careful in doing so. So I'm first of all going to say, by adding 1 and dividing by 4, I end up with sine squared x equals a quarter. Now I'm going to take the square root of this, and I'll end up with sine x equals a half. Square root of 1 over square root of 2. Sorry, square root of 1 over square root of 4 is 1 over 2. But what we've got to consider here is I could have positive a half times positive a half, or negative a half times negative a half. So actually, what I've got here is a positive plus minus in my solution. I've got a positive and a negative option here, which just means we're going to have 4 answers for our angle x here. So if I consider this, my acute related angle, what's my acute angle that gives me sine x equals a half? Or sine of what gives me a half? Well, that's 30 degrees, or pi over 6. And now we get to practice finding those related angles in the other 3 quadrants. Our first one is pi minus pi over 6, which is 5 pi over 6. Then we've got pi plus, which is 7 pi over 6, and 2 pi minus, which is 11 pi over 6. So we've got 4 answers. And of course, these two here, our first two, are what gives us plus 1/2, positive 1/2. And our two solutions here are what give us negative 1/2. But all 4 of those are equally valid solutions. So we've got 2 values that give us 1/2 and 2 values that give us negative 1/2. But because we've taken the square root, all 4 of those are on the table there. One more example here, and we're not going to be dealing with an exact value here. Our first 3 examples have had exact values, as many of these do, but not always. So I've got negative tan x equals 5. Well, I need to make tan x my subject. First of all, I'm going to multiply by 5. So I end up with negative tan x equals 5 over 3. And I'm actually just going to divide by negative 1, so I get tan x equals negative 5 over 3. Now, that is not an exact value, which means we just need to go and find our solutions here and round these. Okay, approximate them. We're going to answer in radians again here, and we're going to restrict with is going to be x between pi and negative pi, which is still one full revolution, or one full 360-degree turn, 2 full tan curves if you'd like, if we consider what their graphs look like. But we're still going to only have 2 solutions here. So our first thing to consider is which quadrants am I working in? I'm still dealing with all 4 quadrants, but I'm just doing them in 2 different directions. Okay, my positive 0 to pi are these 2 quadrants, and then my 0 to negative pi are these 2 quadrants. I get there in the same way, and I'm actually going to have the same solutions in the same positions relatively as if I was dealing with 0 to 2 pi here, but they're actually, one's going to be a positive solution and one's going to be a negative. I'm looking for tan to be a negative here because I've got a negative in the final line here where I've made tan x my subject. So I'm looking at quadrant 2 and quadrant 4. Which means I'm going to have one solution between pi over 2 and pi, and another solution between 0 and negative pi on 2. Let's see how we get those. Okay, well, the first thing to do is to go find our here, because we know we're not going to get an exact value. It's probably the only time we should really be using our calculator as a default. And when I go and find my first solution here, I end up with x equals negative 1.030337. I'm going to say that's negative 1.03 to 3 significant figures. So, as I said, it's about the only time we do end up approximating our trig values for these type of equations, because we normally deal with exact values. So we've actually got our solution here in the fourth quadrant, moving in the negative direction. But what I need to now find is what's my solution going to be in that in the second quadrant, and how I'm going to get there is I'm actually going to add pi to that. Okay, so I'm going to add pi. And the reason I do that is because my first solution, well, the solution I've just found in quadrant 4, is about here. It's about 60 degrees, acknowledging that 1 radian is 57 degrees. We're dealing with about 60 degrees here. So to find that in my second quadrant, we're looking up here, and that's actually a straight line. It does pass through the origin, despite how I've drawn it. And so that means I can just add 180 degrees, or I can add pi because we're dealing with radians. So when I go and find my second solution there, I end up with x equals 2.11, again, to 3 significant figures. So I've got my 2 solutions now. Okay. Now that one's got a little bit to it, especially when we're dealing with that positive and negative domain there. But it's achieved exactly the same way. I make my ratio the subject, I go and find my first solution, and then I consider which quadrants I'm in here. I didn't actually find the acute related solution here because I think it could get us a little bit tangled up. But in fact, my acute related solution would be this one up here. It's not an answer to my equation, but it's that positive 1.03 radians, which is about there. And then, of course, I could go and say pi minus that and take the negative of that to get into the second and fourth quadrants respectively, but we will end up with in exactly the same place here. To summarize, here's the steps we've looked at. We're going to rearrange our equation to make the ratio the subject, find the acute related solution, even if it's not a solution to your actual equation, but just make sure you've labeled this carefully. You could write acute is this, or you could write it off and say and acknowledge that it's your acute solution, but it's not actually one of the answers to your equation. Consider which quadrants our solutions lie in, and then find the related angles for those relative quadrants. Always checking your domain, making sure that your answers fit within the domain that's been given to you. I hope this has been helpful.